So we've spent the last couple of sections seeing sort of the origins of this thing that we call the derivative, and hopefully getting some idea as to how important it is. This whole rate of change thing pops up all over the place, right? One thing that students will often be a little bit concerned about, though, is this kind of fear that these limit calculations that we've been doing to work on derivatives for the past several videos at this point are like all that remains for our calculus course. Like these limit things could get really painful if we're talking about how to work out something for, say, one of the trigonometric functions, or an exponential, something along those lines. So it starts turning into, are we ever going to find a way around having to do every one of these problems as all right, let's take a limit as h goes to 0, and then work through all the machinery there. There are times we do need that kind of machinery available. But as it turns out, no. In case you were worried, that's not where the remainder of this course is going to be. So I now have in my hot little hand a paper copy of a resource you should find on our Moodle page. You'll see this guy right here is labeled Differentiation Rules. Remember, that's fancy math talk for taking a derivative. And I don't call this the differentiation rule sheet. I call it my bestest friend. So pretty much everything we need to know about derivative rules is already sitting on this one piece of paper, or the one PDF when you're pulling it out of our Moodle class. You'll notice right up here at the top we have that limit definition of the derivative that we've been working with for the past couple of sections. So if you need it, it's there. You don't have to memorize it. There's also a whole page of kind of broad strokes derivative formulas sitting there for rules for how the derivative behaves. And on the back side, possibly even more fun, is a list of already given derivatives for some specific functions. So that's pretty neat. As it turns out, we'll talk about one of those in a moment. But so yeah, this guy, he's a big deal. Like I said, I made up a twee nickname for it. So that's kind of the idea here, right? So let's take a look back at one of those velocity examples with the newfound power of our bestest friend sheet here. All right, so previously when we calculated the derivative of this thing, as I said, we appealed to the limit definition to get at that derivative, and that's fine. We should end up getting the same result from what I'm doing here. But in any case, what I want to do is show you how the rules on this bestest friend sheet kind of help us streamline this process. All right, so we've got what we call a quadratic polynomial here, right? We've got some coefficients hovering around. So that's really just some power functions and like a constant, kind of bolted together via addition. So if you notice, a couple of the rules sitting on the front page of the bestest friend sheet say that we can split derivatives up across sums and differences. So it breaks up across adding and subtracting. That makes sense. Limits did the exact same thing. So quick note on the sheet there, it's got that capital D notation for derivative. Sometimes it cuts back and forth. Like I said, D prime. They both mean derivative in this instance. All right. So remember, we've also got that d over dt, or whatever your variable is thing. So I'm going to use those sum and difference rules and break this up into 3 separate pieces. So we've got the derivative of negative 16t squared plus the derivative of 16t plus derivative with respect to t of 32. All right. This guy back here is a constant. And if you look on the back side, or the second page of the bestest friend, the derivative of any constant is in fact 0. So this guy, he just straight up goes away. He's gone. So you'll notice this matches up with the fact that we didn't have that guy hanging around in our limit calculation. All right. Now, the rules on the back of the bestest friend sheet don't specifically mention what to do with this negative 16t squared or the 16t. However, up above those sum and difference rules on the front page, it says that we can pull constants out of derivatives. Again, that hopefully is a little intuitive, because we could pull constants out front of limits. So we've got So we've got negative 16 derivative times the derivative of t squared plus 16 times the derivative of t. Now, you'll recall when we were doing these kinds of calculations in that very first section of the chapter, I built up that table of, isn't it convenient what these derivatives ended up looking like? So that sort of ends up leading into one of the things that calculus students will often end up remembering most out of their Calculus 1 experience. The guy on the back side of the bestest friend sheet that's referred to as the power rule, rule number 2 on the on that list of derivatives of specific functions. We basically get to take our exponent here, slide it out front of our power function, and then subtract 1 from that exponent that we had. So negative 16 times 2t. I'll be a little pedantic and write 2t to the first. We all know I could have just written 2t, but that's fine. Plus 16 times 1 times t to the 0, because yeah, that goes, he goes away. So now I can sort of clean up the notation here, work out some of the multiplication, and I get negative 32t plus 16. So there we go. That's one of the ugliest 6s I've written in the last 5 minutes, but it gets the point across, right? So, and this matches up with what we came up with in the previous video. We got negative 32t plus 16, but we didn't have to appeal to the limit definition because one of those mini Bothans have died kind of things, because, yeah, we've got this list of rules for how to calculate derivatives, which is really awesome. Now, I've still been a little more careful than you might necessarily need to be. I like working through the example very carefully, using the rules, once or twice, just to make sure everybody understands how these things break apart. But I want to take a look at another example so I can kind of show you more often what I would expect to see in this situation. Yeah, so this polynomial is a little bit more intricate than what we just saw, right? I've got it to the 5th power and to the 8th here. The power rule is still going to end up working out. But I don't necessarily require any student who does this to go through the laborious, breaking up the, d over dx. If you need to do it to help you, get a feel for things, that's fine. But it's not going to be necessary as, time rolls on. So if you had gone straight to 5 times, I use the power rule on this guy here, and so x to the 8th becomes 8x to the 7th, minus 2 times, pull the 5 out front, subtract 1 from my exponent times x to the 4th, and then the 6th, well, he's a constant, so his derivative is 0. If you don't write plus 0 at the end, that's fine. It's not obligatory. So I've got this. Now, technically, again, after you've been at it for a while, I don't even mind if you would jump straight to, well, 5 times 8 gives me 40x to the 7th, and then 2 times 5 is minus 10x to the 4th. So I'm totally fine with that in general. This is, perfectly sufficient in my book. So, just to make sure, like I said, if you need to break down, the things with the properties to make sure you see how everything flows, that's fine, but it's not mandatory. All right, so we got some power functions here. We've done a couple of these. I can work out one more real fast just to give us, kind of a different experience here. So let's see. We'll have, 10x to the 13th plus 8x to the 11th minus 6x to the 6th, just to play around with this. So if you had gone straight to using this, all right, 13 times 10, that's 130x to the 12th. 11 times 8 gives me 88 times x to the 10th, minus 6 times 6 is 36, x to the 5th. If you would just call it right there, again, I'm totally fine with it. I mean, if you'd like, you could do a little algebra here, clean this up, do some factoring, pull off, I guess an x to the 5th. All those numbers are even, so you can at least pull off a 2, maybe some other constants. But yeah, that's the sort of thing that I'm expecting to see, when it comes to calculating derivatives of, say, a polynomial. All right, so we've got a few examples in the books now, but they're all polynomials. What happens if we have to deal with a function that, say, isn't a polynomial? We'll pick up with that in another video. So, yeah, hang on for a moment.